So today's topic is duobinary signaling and correlative coding. So duobinary signaling actually is a scheme for transmitting R bits per second using less than R by 2 hertz of bandwidth. Actually, I was trying to explain you on the other day the converse kind of thing of Nyquist theorem, in which Nyquist sampling theorem says that the sampling rate should be at least twice the maximum frequency component. The other way to look at this theorem is that maximum achievable rate is twice the bandwidth of the channel, right? So if B is the bandwidth of the, if for a band limited channel, if B is the bandwidth, then you can transmit 2B symbols or information per second, right? But duobinary signaling is used for transmitting R bits per second using less than R by 2 of hertz of bandwidth. Actually, Nyquist theorem, if you apply the Nyquist theorem, so R bits per second will be sent using R by 2 hertz of bandwidth. But this scheme is there basically to send R bits per second using less than R by 2 hertz of bandwidth. So that's what is explained in point number 2, right? So now how it is impossible, how it is, possible. Nyquist theorem for zero ISA condition says that if the theorem that I was trying to explain was that when R bits per second are sent in R by 2 hertz of bandwidth, so this is actually the Nyquist theorem for zero ISI. But if we try to introduce some ISI in the system, right, some known ISI, known intersymbol interference in the transmission, and since we know how much, what is the amount of intersymbol interference introduced in the transmission, so the same can be removed from the receiver, because we already know what is the status of ISI in the transmission, and so we can apply the inverse process at the receiver to mitigate that effect. So this result implies that duobinary pulses will have ISI. However, the ISI is introduced in a controlled manner so that it can be subtracted out to recover the original values. So that's the basic introduction or basic background behind the duobinary signaling. Now let the transmit, how do you represent the transmitted signal? So we have already done this representation, but just put in a different way. So xt is the transmitted signal. K is some index going from -infinity to infinity. Dk are the, this dk is basically the bits, either 1 or 0. Qt minus kt is the pulses that will be used to represent these pulses, these bits, right? So dk can be 0 and 1. So that means dk will be either 0 or 1, means it will be the bits, right? And q will be bits, I mean 1 bit at a time. And qt minus k capital T is the pulse shape that is used to represent the bits. So dk, the set of dk are the bits. Qt is the transmitted pulse, where capital T equal to 1 by r is the bit period. The pulses qt are chosen such that there is no, now this point is when the Nyquist theorem is fulfilled. The pulses, in that case, the pulses qt will be chosen such that there is no ISI at the sampling instances, because we know that if we choose raised cosine pulses, and if we select the spectrum of all the pulses in such a way so that the summation of all the spectra becomes flat, so there will be no ISI in the system. So if we select qt in such a way that there is no ISI present at the sampling instances, so what can be that possibility? If you, this small t has to be equal to k capital T, that means k is equal to 0 plus minus 1. So at the sampling instances, this t should be equal to kt. The pulse should go to 0 at t equal to kt. Kt means k can be 0, 1 or -1 +2 and -2, +3 and -3. So at that instances, what will happen? The pulse will go to 0. Once the pulse will go to 0, there will be no ISI present in the transmission. But since I'm saying that duobinary signaling is basically that we are introducing some kind of intersymbol interference into the system. So in that case, the QT, what is the pulse should be? It should be equal to. So this is again the case when the ISI is going to be 0 at ISI is going to be 0 and the pulse shape is going 0 at. So it will be k equal to 0. It will be 1. Otherwise, it will be 0. Correct. NRZ is one such case in which the NRZ case will actually fulfill the Nyquist theorem for 0 ISI. But what is the other case? So this is the point number 1 here in this slide actually depicts the case for the duobinary signaling. Now, if you look at this expression of the pulse, QKT equal to 1. In this case, it was 1 only at k equal to 0, right? But in this case, it is 1 at k equal to 1 also. So that means the pulse is extending beyond certain limits, right? If pulse is extending beyond the sampling beyond this first sampling instant, at that, so what does it tell? It tells us that we are introducing some kind of intersymbol interference into the system. So by introducing some ISI into the system, we can achieve R bits of transmission rate with less than R/2 bandwidth. So that is the advantage of duobinary signaling. If we do not introduce any ISI deliberately into the system, so what will happen? We will be able to achieve R bits per second only with R/2, at least R/2 hertz of bandwidth. But we can achieve R bits per second information rate with less than R/2 hertz bandwidth with the known value of the ISI introduced into the system. So that's the advantage of duobinary signaling. And there will be some treatment done. Just a minute. There will be some treatment done on these bits. We will see that what is the treatment. Let's look at that, how the encoding will be done. Now, duobinary signaling, detection of data by controlled ISI. So that I have just explained you. Sample of the received filter. So this is YTI is equal to BTI plus NTI. YTI is the sample of the received filter. So at the receiver, this is the sample received. BT is the bit value that is transmitted plus NT some noise, right? So YTI can be put it equal to AI plus AI minus 1, right? So BTI will be equal to AI plus A minus 1 basically. So what is AI? Amplitude of the transmitted sequence, the present bit. What will be AI minus 1? The amplitude of the transmitted sequence, the one interval behind the present bit, right? So AI will be equal to the summation of the present bit and the previous bit, right? So NTI is the Gaussian noise. So AI can be either +1 or -1, this AI, the amplitude. So how the bits will be represented? Either by +1 or -1. +1 will be represented with, +1 will be used to represent, let's say, 1, and -1 will be used to represent 0. So it can be either +1 or -1. And what I'm saying is that what is BTI equal to? It is AI plus AI minus 1. So BTI can be, what values BTI can achieve? It can have +2, it can have -2 or 0. There can be only 3 cases because AI can be 1, this can also be 1, it will lead to 2. AI can be -1, it can be -1, it can lead to -2. Any one of the 2 values will be +1 or -1, it will lead to 0. So there can be only 3 values, +2, -2 or 0. So if we neglect noise, let's say, right, and YTI will be equal to AI plus AI minus 1. So that means AI is 1 bit, right? AI minus 1 is the second bit. So it will represent the two bit combinations. It can be 0, 0, 0, 1, 1, 0, and 1, 1. Excuse me. So 0, 0 will lead to minus 2 volts. 0, 1 will lead to 0 volts because 0 will be minus 1 and 1 will be plus 1. It will lead to 0. 1, 0 will lead to 0 and 1, 1 will be 1, 1 will lead to 2. So that is Duobinary encoding. This is how we start the Duobinary encoding. And since this equation YTI is equal to AI plus AI minus 1, we can have a different representation or alternative representation of this equation. It says that CK is equal to AK, C subscript K equal to A subscript K plus A subscript K minus 1. This is the alternative representation of the equation given above. You will find that this equation is used in many of the books. In duobinary signaling, 2 successive bits are used for evaluation. This process is also known as symbol by symbol detection of data or duobinary signaling or correlative coding. Correlative coding, why? Because we are trying to compare the two present and the previous bits. Signaling rate, I have already talked about the signaling rate. So let's formally look at what is duobinary signaling. So this will be the block diagram of the duobinary encoder. This is, let's say, AK. AK is basically, I have put AK, I have equated AK to AI, which I was just trying to explain. AK is the present bit, AK minus 1 is the delayed bit. So AK, it is delayed by 1 bit interval. So, and these will be added. So that means it will be AK plus AK minus 1, right? At this point, after summation. Now, if we do NRZ encoding, AK is equal to plus 1 when BK, which is the bit, right, equal to 1. When the bit is 1, your AK value will be plus 1 volt, plus, I should not say volt, but it will be plus 1. And when BK, which is the bit, if it is 0, AK will be equal to minus 1. All right. And we send it through the Nyquist channel and sample it, then we get CK. I have just explained what is CK. CK is equal to AK plus AK minus 1. So the encoder is the block diagram, which is shown here, and converts into encoder. Actually, this at the input of the encoder, it takes 2 values, except sequence, right? And either it is 1 or 0 or plus 1 and minus 1 in terms of levels, but it transmits 3 levels, plus 2, minus 2 or 0, right? So CK will be equal to AK plus AK minus. So how to reconstruct the signal bag? To reconstruct the transmitted signal, let's consider AK hat. AK hat will be the estimate of the AK. So estimate, what will be the estimate of AK? It will be CK, which is the output of the encoder, minus AK estimate K minus 1. So let us try to solve duobinary signaling using an example. So this example tells me BK is equal to, let's say this is the bit stream, 0, 0, 1, 1, 0, 1, and 0, 0. Let's say this is the bit stream. So what is the first step? The bits will be represented in terms of the levels, plus 1 or minus 1. So 0 will be represented with minus 1, 0 is minus 1, this 1 is plus 1, minus 1, plus 1, minus 1, and minus 1, right? So this will be my AK. What will be CK? Because at this point, I don't have AK minus 1, so I will put a dash here. So at this point, this will be my present, this will be my AK, and this will be my AK minus 1. Minus 1 added with minus 1 will be minus 2. So this is my AK, and this is my AK minus 1. Plus 1 added with minus 1 will give me 0. So in this way, if you go on adding the present bit with the previous bit, you will find these CK. Now, how to obtain AK hat? How to obtain the estimate of the AK? So I can put, how to get this AK hat? I have to, if CK is received, Now this will be CK, right? Here, let's talk about this only first. This is my CK, it is -2, right? And let's suppose that this is -1. All right. So in that case, CK is -2 and minus of at this point. If you look at this point, I assume that my AK -1 at this point, AK -1 hat will be -1. So -2 minus of this -1 will give me -1 because CK is -2 here. What will be AK -1? AK -1 is also -1. So if I put -1 here, this sign will become plus. So -2 plus 1 will give me -1. All right. So this will be my CK for the next bit. It will be 0. What is my AK -1? AK -1 is -1 here. So 0 added with 0 subtracted with -1 will give me +1. This is +2 here. CK is +2. What is AK -1 hat? It is +1. So 2 minus 1 will be 1. So like this, you will go for AK hat. This is the decoding that I am trying to do. So this equation is for the decoder. How you will recover the data back. So how do you if AK hat is -1, it will be 0. It will represent 0 bit, and if AK hat is +1, it will represent bit 1. So it is -1 0 -1 0 +1 1 +1 is 1 again, and so on. So if you compare this transmitted bit information with the received bit information, they will be same. So this is known as this first line of this matrix actually are the bits. The second line of this matrix are the amplitudes. The third line of this matrix is encoding done by this. If you look at this block diagram, how do you do the encoding? Encoding is done CK equal to AK plus AK -1. That's why it is known as Duobinary signaling. And how you will recover the signal back? You will recover the signal back in terms of AK hat. This is my AK hat. How do you recover it? CK minus AK minus the previous estimate. So to start with, I don't have the previous estimate, but let's assume it is -1, right? So then you can follow further and you will see that you will be able to decode the information properly. Now, in this duobinary signaling, there is one problem. What is the problem? If CK is received with error, now if CK, which is the encoded information, now it will be transmitted through the channel. So once it is received at the receiver, what can happen? If it goes in error, if CK is in error, then what will happen? AK hat will have error and will propagate at the output sequence. So this is one of the drawbacks of the duobinary signaling, that if CK is received with error, so the error will propagate further. Now, what is the remedy to this problem? The remedy is the precoded duobinary signaling. So we will use a precoder before we do the. So what is a precoder? So this precoded duobinary signaling for controlled ISI is also known as differential encoder. So let's look at this. So BK are the bits, right? You will use an XOR gate here, right? So DK is the output of the XOR gate. So it will be fed back with 1 bit delay. It will become DK -1. So what are the inputs to the XOR gate? One is the present bit and one is the delayed output of this XOR gate. So DK -1. So what is DK here? DK is actually BK. This is my BK. BK XOR with DK -1. So this is the delayed version of this DK output. So what are the inputs to the XOR gate? BK and DK -1. So what is the output? Output is DK. So and DK will be 1. We know that how the XOR gate operates. If BK or DK minus is 1, if one of them is 1, the output, this DK will be 1. If both of BK and DK -1 are either 0 0 or 1 1, so output will be 0. All right. Now, so DK is applied. After that, after this is done here, it is applied to a level shifter. So what dk is applied to a level shifter and its output is ak. So the output of the dk is applied to the level shifter. The output of the level shifter is ak. Right? It's a bipolar output. If dk is equal to 1, now if this bit is equal to 1, what will be ak? AK will be equal to 1. If dk is equal to 0, what will be AK? AK will be equal to -1. So at this point, we will get AK. After AK, we apply to a summer and we apply also the delayed version of AK. So from here, the AK is delayed by 1 bit interval and this becomes the second input to the summer. So AK and AK -1 goes to the summer and CK is the output, encoded output. So this is the AK obtained, right? Now AK is applied to a duobinary encoder. This is basically duobinary encoder, and this part of BK and DK -1 going to an XOR gate, this part is actually the pre-coding. This is known as pre-coding done in the duobinary signaling. So that's why it is known as pre-coded duobinary signaling. Right. So this is what we were earlier doing, the normal duobinary signaling. So AK is applied to a duobinary encoder and its output is CK. The output of this portion is CK. Now what is CK? If you look at this diagram, what is CK? CK is AK plus AK -1. CK is AK plus AK -1. Now if CK is 0, if we obtain here 0, what if CK is equal to 0, if BK is 1, we will obtain if CK will be equal to 0 if BK is 1 and CK is equal to ±2 if BK is equal to 0. So let's take an example actually that will make the things more clear. So this is the decoder part. Let me explain the decoder first. Decoder, you apply this CK to the decoder and you apply it first to the rectifier. Rectifier means take the positive side of the CK, that means the modulus value of CK, and then make a decision. How do you make a decision? You make a decision with BK equal to 1 if mod of CK is less than 1 and BK equal to 0 if mod of CK is greater than 1. So let's take an example here. Okay. In this matrix kind of arrangement, so first line is the BK. So we take an input 0, 0, 1, 0, 1, 1, 0. So let's try to encode it. How do you encode it? First, because you have to apply it to the precoder, so bits will go into the XOR gate. So let's look at the example. DK -1, right? Let's say this is my DK. Let's suppose that 1 is here. So it will go here. It will become DK -1, right? Just making an assumption that it was 1 here at DK, and we go and it goes as DK -1 at this point. Now BK will be XORed with 1 to give you the next to give you DK. So 1, 0 XORed will give you 1. This 1 will go here. So 1 XORed with 0, again 1. This 1 will go here, becomes DK -1. 1 XORed with 1 is 0. 0 goes here, becomes DK -1. 0 XORed with 0 is 0. So in this way, you will obtain DK. What is the next step? After you obtain DK, you apply it to a level shifter. What is the level shifter? Level shifter is if DK is 1, AK will be equal to 1. DK is equal to 0, AK equal to -1. So what will be AK? It will be 1, so you will put it 1 here, 1, 1. 1 goes to 1. If it is 0, it will be -1. 0, it will be -1, and so on. So you will obtain AK. And then you apply it to the duobinary encoder. That means you obtained AK and then delayed by 1 bit interval, you will get AK -1. And then if you add, you will get CK. So that's the next step actually. So what is AK -1? So this is the bit AK. If you delay it by 1 bit interval, this bit will come here, it will be A1 here, and so on. So the whole AK sequence will be delayed by 1 bit interval and you will get AK -1. So once you start adding AK and AK minus 1, you will get CK. So 1 plus 1 is 2, 1 plus 1 is 2, minus 1 plus 1 is 0, minus 1 minus 1 is minus 2, and so on. So that's how you obtain CK. And then you transmit. So this part is the decoder part. You obtain CK, apply it to the rectifier. That means you take the modulus of this. So this is my CK, take the modulus. So every value will be positive value, 2 to 0. At this minus 2 will become 2, and so on. And how do you make the decision? The decision is made if CK is less than 1, it will represent bit 1. If CK, modulus of CK is greater than 1, it will represent bit 0. So this is 2, it is greater than 1, so it will be 0, 2 greater than 1, 0, 0, which is less than 1, so therefore it is 1, 2, which is greater than 1, right? So it will lead to 0 and so on. So 0, 0, 1, 0, 1, 1, and 0. If you compare it with this, you will find that this is the same sequence as was transmitted. So this is known as duobinary signaling, right? In which the advantage is taken by introducing certain amount of intersymbol interference and then doing the reverse process at the receiver end in the same proportion, so that the effect of the known ISI can be overcome. All right. So this finishes the duobinary and correlative coding part. I would like to do one more actually left portion in the syllabus. Probably it is there in the first chapter. So let me just stop sharing this presentation, and I will share one more presentation in which I will discuss the T1 and E1 systems. And let me just stop sharing it and share the next PPT, and then I will explain. Okay. So this is time division multiplexing. And basically, I will explain what are T1 or E1 system. In your syllabus, probably it is mentioned only T1 and E1. So I will not go into details of T2, T3, and T4 systems, because it's just the hierarchy, higher hierarchy of versions of the T1. Means T2, more number of multiplexing lines are included in T2 system, then T3 system, and T4, and so on. Let me explain you the basic concept of time division multiplexing first. Now, so what is, it is the Bell system actually proposed this T1 carrier system actually in 1962. T1 is a member of the group of carrier systems developed by AT&T Bell Laboratories for digital transmission of multiplexed telephone calls using pulse code modulation and time division multiplexing. So let's see what's the process. This system, in which 24 telephone channels are there, this system is actually T1, or the higher version of this will be higher. I mean the hierarchical, in the hierarchy, higher system will be T2, then T3, and then T4. So these systems are actually used in USA. E1 system, E2 system, E3 system, E4 systems are actually used in India or Europe, right? But the basic concept remains the same. The only difference is that here in T1 system, you have 24 telephone calls, meaning by there will be 24 channels. Whereas in the case of E1 systems, you will have 30. Okay, this is a good slide to make the comparison. So this is T carrier data rates, and this is E carrier data rates. What is this zero level? Zero level means only one channel can be there. It is 64 kilobits per second. So what is the bandwidth allocated to one telephone call or one transmission happening between source and destination? That means one call or one channel. The bandwidth is 64 kilobits per second. In the e-carrier system also, the bandwidth remains the same, which is 64 kilobits per second. But what is the first level, which is called the T1 system? In the T1 system, there will be 24 channels, whereas in the case of E1 system, there will be 32 channels. So let me talk about T1 and E1 first, and after that, I will a little bit talk about T2 and other systems also. So what was, to start with, what is time division multiplexing? Time division multiplexing says that this is regarding the telephone systems used, right? For example, in Thapar University, there is an exchange connected, the internal exchange. So how the communication will be done between various connections. So this is a basic setup for the specifications for that kind of system. All right. So, and how the bit transmission will happen. What is the frame structure of that bit transmission? So let's look at that. The bit one, there will be a total of 193. One frame will include 193 bits, right? And how much time it will take? 122 microseconds per frame. That's the kind of speed at which the bits need to be transferred, right? So 193 bits will be there. So how these bits will be stacked in this time. So first bit is actually bit one is a framing code. It's related to the framing information, framing code. Now, as I said, in T1 system, there will be 24 channels, channel 1, channel 2, 3, 4, and 24. So there will be 24 channels. Each 24 channels means at one time, because it's all digital system. So for example, there are 24 people making calls to one another, right? 24 people, there are 24 live calls running between source and 24 sources and 24 destinations. What will happen? There will be analog to digital conversion at each call, right? So we know the process. The sampling will happen, the quantization will happen, and the encoding will happen, because this is basic PCM system. For every call, there will be sampling, there will be quantization, and there will be encoding. Now, what will happen is that, so we also know that every sample of every call will be encoded with a certain number of bits. But in T1 system, every sample will be encoded with 8 bits. That's the specification. So every sample value will be encoded with 8 bits. So if you look at channel 1, how many bits are there? 1, 2, 3, 4, 5, 6, 7, and 8. This is the sample value actually. Every sample value will be encoded with 8 bits. So this 1 bit is the frame bit, the start of the frame bit, right? So these are the 8 bits for one channel, 8 bits for second channel, and so on. So in this way, there will be 24 channels. When the turn for channel 1, the call which is happening at channel 1, it will transmit one sample with 8 bits. Then within this 122 microseconds, what will happen? First call has transmitted first sample with 8 bits. Now the first call will not transmit the second sample. It will wait. What will happen? The second call will transmit its first sample. Third call will transmit its first sample, and so on, going up to 24th call. 24th call will transmit its first sample. So first sample of channel 1, it will wait now. It will allow in this time channel 2, channel 3, channel 24. That's why this is known as time division multiplexing. The time is because channel 1 has sent its first sample only. Now it is waiting. Waiting for what? Waiting for other channels to be multiplexed, right? Between the first sample of channel 1 and the second sample of channel 1. How many channels will be embedded between two samples? 24 channels, as I'm saying. So channel 1, 8 bits, channel 2, 8 bits, channel 3, 8 bits. It's the time which is being slotted, time which is being multiplexed. Correct? So if you look at the how many bits are there for channel number 1, 8 bits, how many channels are there? 24. 24 into 8, it is 192, and this 1 bit for the start of the frame bit. So that's how it becomes 193 bit frame. What is the time period of this bit frame? It is 122 microseconds. So how many in 122 microseconds, how many bits will be transferred? 193 bits will be transferred. In 122 microseconds, how many bits will be transferred? 193 bits will be transferred. But if I try to calculate how many bits will be transmitted per second, it will come out to be 1.544 megabits per second. So that's the data rate which can be used in T1 type of systems, right? Whereas in the now this is the time division multiplexing. So what will happen? There will be 1, 2, 3, 4, 24 channels. So first it will allow the first channel to transmit first sample of the first channel. Then it will actually clockwise rotate, right? This is a circular kind of switch. So it will again come back to the first channel only when it has traversed through all the rest of the channels. So this is known as time division multiplexing, right? Then the signal is applied to coder, signal processor, it goes through the medium at the receiver end. Also there will be some processing done, decoder, and there will be the demultiplex, because at what time which channel is being used to transmit, so everything will be synchronized. So at the receiver also this will be everything will be synchronized, and you pass it through the filters, 24 filters. You will be able to separate out the calls. Why this type of multiplexing is needed? Because you are transmitting 24 calls, you are receiving 24 calls, but the medium is only one, right? So that's why you are trying to multiplex through time. There is one more type of multiplexing which is known as frequency division multiplexing, where you will be, for every call, you will be superimposing it to different frequencies, right? And you transmit through common channel. At the receiver, you pass only, you recover the signal through those frequencies only, right? And you can demultiplex the signal. But let's not talk about the frequency division multiplexing at present. Some other time, maybe that is also included in your syllabus. We'll talk about that. But let's talk about the time division multiplexing at present. So time is being multiplexed, right? And received. So this is T1 kind of system in which 1.5, what is the data rate achievable? 1.544 megabits per second. I have tried to explain you how this 1.544 megabits per second data rate has come. But in E1 systems, 2.04, the data rate will be 2.048 megabits per second, because there will be 32 user channels, but every sample will be coded with 8 bits only. In the same way, this is P1 system. This is known as multiplexing. Actually, in most of the telecom companies, you will see that if you happen to visit any telecom company, you will see that there will be mux division in every telecom company. So mux division is the importance of mux division is related to what I'm trying to explain here, right? So how you implement the system, that is handled by the mux division. The second level of the multiplexing is that when one T1 system will have 24 channels, there will be 96 T1 type of systems, right? So what is the, so this is the data rate achievable, correct? The total will be, sorry, there will be 20, in T1 system, how many channels are there? 24 channels are there. There will be 4 T1 type of systems in T2. That's why there are 96 channels. And in E2 systems, how many users are there in E1? 32. So 32 into 4 will give you 128. So how much data rate you are achieving? 2.048 multiplied by 4, 8.448. 1.544 multiplied with 4 will give you this 6.312. Right? So that's the hierarchy level. Now, if in the same way, you try to get T3, T4, and T5 systems. And these are the, I'm giving you the specifications of the number of channels which can be accommodated in various carrier levels. The level 1, which is T1 or E1 systems, T2, T3, T4, and so on. Right? T1 is mostly prevalent in North America, whereas E-carrier systems, T-carrier systems are North America or American kind of countries, whereas E-carrier systems are prevalent in Europe or India also. So this is basically the specifications which correspond to the PSTN network. What is the PSTN network? It is a public switched telephone network. What is that? Public switched telephone network is the BSNL exchange. Nowadays, it's the BSNL exchange. In older days, what used to happen was there used to be a old kind of building, and huge exchanges were installed in those buildings so that the telephone connections can be made with each other, right? And so these were the systems that were installed there. But nowadays, since mobile phones and other things are happening so fast, so maybe PSTN networks are losing their charm, but these are related to the PSTN network, public switched telephone network. So this was there in your syllabus. I just felt that I must complete this part because this was written in your first chapter only. So now on, everything is clear up to the point of probability of error calculations, right? From next lecture onwards, I will come back to the probability of error calculations for other modulation schemes, which included the quadrature amplitude modulation and the phase shift keying. And I will also describe about the decision region. How will you make the decisions based on the decision regions in favor of any bit combinations which are transmitted from the transmitter side. So if any questions are there, then please ask. Varun? Any questions?
No, sir. No, sir.
Archita, any questions?
No, sir.
Okay, I will end this lecture, and I have done the recording, so I will upload on LMS also. Okay.
So will PPTs will also be uploaded of this topic?
I have uploaded all the PPTs. Are you able to get or not? Hello?
Sir, PPT भी upload होएगी ना अभी इस topic की LMS पे?
101%. I am uploading notes. I mean, these are notes only, PPT. It will be uploaded, sure. Just now I will upload.
Okay.
Okay.
Okay, sir.
Thank you. Thank you.